Today in Intermediate Algebra, we look at section 6.4, where we start talking about geometric sequences. You can see that the three objectives for this section over the next couple of days is that I can find the explicit and recursive formulas for geometric sequences. I can translate between recursive and explicit formulas for geometric sequences, and I can construct exponential functions to represent geometric sequences. Hopefully that actually sounds somewhat familiar because everything in here is the same as something we did in the first chapter we did this year when we did arithmetic sequences, but now we're replacing it with the word geometric. So we'll learn the difference between those two things as well. So as our warm-up, we're actually going to talk a little bit about that. Here it says a stadium the seating plan is designed for section 12 of a new stadium. Okay, the picture is above. And it wants you to describe the pattern. So take a second and look at how those seats change row by row and figure out what the pattern is. Hopefully you're able to see that the first row, row A, had 2 seats, and the next row had 5, then 8, and 11, and then 14. Okay, so as we look at this pattern, what we can see is that every time we go up a row, we are adding 3 more seats. This should ring a bell. So if we're adding 3 more seats, what we learned earlier this year is that that makes this an arithmetic sequence. Okay, so that makes it arithmetic. And as a reminder, we talked about the recursive and explicit formula, but the explicit formula is the one that's much more user-friendly. In order to write the explicit formula, we needed the first term, a sub 1. Well, that would be the number of seats in the first row, so that's 2. We would need D, which was the common difference. That's how much every row is going up by. So that's that plus 3. And then we learned the formula for the explicit formula for an arithmetic sequence. And that was a sub n equals a sub 1, the first term, plus D times n minus 1. So once we knew these two things, we substituted in. So a mathematical expression would be 2 plus 3 times n minus 1. Now back then we did talk about how we could simplify that, but we're not going to worry about that as much here. The reason we like this is because then we can figure out things for the future. So for example here it says row Z of section 12 must have at least 75 seats, so 75 or more. If that pattern continues, does the seating plan meet the requirements? Please justify. Well, first we'd have to figure out what row number row Z was. So row A was 1, B was 2, C was 3, 4, 5. These represent my n values. So if I can figure out what number row Z is, then I would just substitute that in for n. I know that there's 26 letters in the alphabet, so that makes the last letter Z, 26. So for this problem, they wanted me to find a sub 26, the 26th term. So I use this explicit formula, 2 plus 3 times 26 minus 1 gives me 2 plus 3 times 25. 2 plus 75, which means in the zth row there is 77 seats. And again, the goal was that it must have at least 75, so yes, this met the criteria because 77 is more than 75. All right, so that was just actually a review of arithmetic sequences, and throughout this section we're going to talk more about how that compares to what we're doing here. But in this section, we are focusing on this thing called a geometric sequence. And the biggest difference is that when it's arithmetic, you're adding to get to the next term. With a geometric sequence, you are multiplying to get to the next term. So a geometric sequence is a sequence in which each term after the first is found by multiplying. That's the key. Okay, so multiplying the previous term by a common ratio. So we use this term common ratio when we're talking about multiplying. Okay, it was common difference when we're adding and subtracting, common ratio when we're multiplying. So for example, if I have 2, 6, 18, 54, so on and so forth, to get from 2 to 6, I'm multiplying by 3. To get from 6 to 18, I'm multiplying by 3, which means my common ratio is 3. Now you might think this sounds very similar to what you were doing in section 6.2, for example, where you were looking at exponential growth compared to linear functions. And that's actually true, because we learned back when we were talking about arithmetic that those align with linear situations, and geometric sequences will align with exponential. So it's going to be very similar. The difference here is that we are starting with the first term instead of the initial amount of 0. Okay, so that's the difference between the geometric sequences and just the exponential growth you looked at. All right, so this says determine whether the following sequences are geometric or arithmetic. Okay, so you're looking for that common ratio. Quick and easy way to find this, Miss Nosworthy showed this in a video, is you can take the second term divided by the first. So this has a ratio of 2.2. If I did that, I would need to get the same thing when I do 4.84 divided by 2.2, and I do in fact get 2.2. I could test more, 10.648 divided by 4.84, I get 2.2. So since I'm getting the same thing every time I divide a second term by the previous term, I would claim that this is geometric. So why don't you pause the video and check the other two, see what you think. All right, you could have tested out what you got when you divided these, but as I look at these, I notice that I'm adding 1.5. So you're really looking at the difference. Am I adding or am I multiplying? Since I'm adding, this one is arithmetic. And for your last one, if I do a negative 12 divided by 16, I get negative 0.75. If I do a 9 divided by negative 12, I get negative 0.75. So if you keep going, you do get negative 0.75 every time. So this one is geometric. And with these sequences, you do have to be careful, because sometimes if it is alternating signs, that's okay, because that just means that your R value is going to be negative, which is okay for a geometric sequence. Okay? All right, now that we've talked about what a geometric sequence is, now we need to learn how to write the equations of one, or the formulas, both recursively and explicitly. So the recursive formula, similar to what we learned back when we were talking about arithmetic, that's where we need to know the first term. I'm going to add that in there. You would always have to figure out what the first term is, and that would have to be part of the formula. Okay, so you'd write down a sub 1 equals whatever that first term in the sequence is, and then it's a sub n equals r, which is the common ratio. So a sub 1 we should add in as the first term. A sub n is the nth term. So in the future, when we find bigger terms, we're going to put that number in for n. And then probably most difficult for students is this a sub n minus 1. And just as a reminder, that represents the previous term. So basically, if you're thinking about something recursively, I think about rewind. Okay, so you're taking that r value and rewinding back. You're multiplying by the term right before to get your next term. Okay, so if we're given a sequence of numbers like we are here, 8, 12, 18, 27, 40.5, and so on, and it asks me to write the recursive formula, the first thing I need to identify is my a sub 1. Well, that's my first number. Then I also need to find my r, which remember would be the second term divided by the first term. 12 divided by 8 is 1.5, but just as a tip, Pearson always makes you write in the fraction from everything I saw anyways, so you need to reduce this. Both of these are divisible by 4, so it's 3 halves. Okay, and then I would do 18 divided by 12, both are divisible by 6, I get 3 halves. So I'm going to use r is 3 halves. Again, if you're doing it on paper, 1.5 is just fine, but Pearson does almost always ask you to put it as a fraction. So when I go to write my recursive formula, I write a sub 1 equals, that was the 8 that we found as the first term. I copy down the a sub n equals, I put my r in, 3 halves, parenthesis, and then I just copy down that a sub n minus 1. I don't have to do anything with it, it's just there. So that would be your answer. Okay, if you feel comfortable, pause the video now and try 1 and 2. If you would like to see one more example, I'll do the first one first, and then you can pause and try the second one. So again, when I'm asked to write the recursive formula, I figure out my a sub 1. So I write that down right away. A sub 1 equals 3072. I know then I write down a sub n equals, I need that r value, and then I'm just going to write it times a sub n minus 1. Okay, so the recursive formula, remember you're finding a sub 1, finding r. To find r, I would do 768 divided by 3072. When I did that, I got 0.25. So with big numbers like this, I would get the decimal first, 768, I get 0.25. But again, Pearson's going to say I can't put in a decimal, so I need to know that 0.25 is the same as 1/4. Okay, you could put 0.25, that's 0.25 1/100ths, or 25 1/100ths, so you could rewrite it as 25 over 100 and then reduce that way. Okay, but it is 1/4, so we want to practice that. All right, now pause the video if you haven't already and make sure you do that for the second one. All right, for this one, you should have had a sub 1 is 784. And then I just wrote it as a sub n equals negative 1.1 times a sub n minus 1. I know I just told you to make them fractions, but this one was a little trickier because the numbers were so big. One example, I take the second one, negative 862.4 divided by 784. Gave me negative 1.1. I do check another one just to make sure that they're not tricking me and it's not arithmetic or not geometric. But if they're telling me it's geometric, then I should be able to just check a couple. Okay. Now, one last side note about recursive when it comes to Pearson. There's a chance that when you type it in, they actually have you show it two ways. So when they ask you to write the recursive, sometimes they write a little a sub n. In that case, you want to write it like this. So if I was going to write the 1/4 times a sub n minus 1, you might need to play with this a little bit, but when I was practicing your guys' homework, there were a few times when they gave me a capital A parenthesis n, and they were asking for the recursive formula. And when I typed it in like this, they told me I was wrong. But then in that box, remember when you get something wrong in Pearson, it gives you a box and explains to you kind of what they're looking for. And in the box, they actually said to type it in as when it was written this way. This was the only time it was when they used the capital A. They said to write a capital A parenthesis n minus 1, so no subscript, times r. So when I typed this in and it said it was wrong, it gave me a box that said this is what they're looking for. So then I retyped it in and I typed a capital A parenthesis n minus 1 parenthesis, and then I typed in 1/4, and they said that one was right. Okay, so I believe, and this is just my guess, is if they start with the a sub n with the lowercase a, that's when I was getting it right when I would type it in this way. It was only on one problem, I think, where they had the capital A of n, and they wanted it in that form. So I apologize for that. I wish it wasn't that way, but in order to find enough good problems, I think I had to leave one of those in there. Okay, so that's recursive, the rewind, but the downside of recursive is that you always need the previous term. So it's okay to use recursive if you're finding the first few terms, but if you ever want to find like a higher number term, like the 8th or the 9th or the 10th or the 20th, you want the explicit formula. Okay, so remember, the explicit formula is the one where you get to just plug in for n. So you can use to find any term n. That's why we like it. So even like the 100th term. Okay, so this will be a sub n equals a sub 1 times r to the n minus 1. Well, a sub n is still the nth term, just like we wrote down before. R is still that common ratio. What are you multiplying by? A sub 1 is still the first term. And then just remember, n is the term number that you're talking about. So if you want to find the 50th term, you plug 50 in for n. Okay, so again, the reason we would use this is if it asked me to find the 10th term in the sequence, I don't want to just keep multiplying. I could still get there, but it's annoying. So in order to find the 10th term, I'm going to use the explicit formula. But remember, for the explicit formula, just like the recursive, I just need a sub 1 and r. So once again, my a sub 1 is 8. My r is 12 divided by 8, which is 3/2. This is actually the same sequence we did the other way. So we went through already and divided them all. Okay, so we found this in the recursive formula. So if I'm using the explicit, I would write a sub n equals that first term, which is 8, times r, which is 3/2, to the n minus 1. That's my explicit formula. Once I have that, if they want me to find the 10th term, I would just type in 10. So a times 3/2 to the 10 minus 1. Now you could type all that into your calculator as is. You are going to need your calculators for this. I, however, and Ms. Nosworthy actually showed you, so 8 times, she showed that within the parentheses to do the fraction, just do 3 divided by 2. I would type it into the 9. Otherwise, if you do it to the 10 minus 1, make sure you put parentheses around it. She also taught you how you're going to use the caret key to get to that, or that might have been Miss Krupstead earlier. All right, so I just typed all this into my calculator, and I got 307.55. So that's what that would give me. Okay, so I want you to pause the video and see if you can figure this one out. We're finding the 12th term, which again, we should hopefully use the explicit formula. Okay, as soon as I want to find that, I know I need the explicit. So the explicit formula, remember, is a sub n equals a sub 1 times r to the n minus 1. So you need to find the a sub 1 and the r, but they give it to you in a little different way. So I want you to pause and see if, based on what we learned about the recursive formula, you can figure out what the first term in r is to plug it in. Okay, so hopefully as you were looking at this, you saw the term initial condition is 3. Initial would be starting amount, so this would be a sub 1. Okay, so my a sub 1 in this case is going to be 3. And then the recursive formula, remember, it's always r times a sub n minus 1. So they're actually giving me my r, that's 6. So we can convert from recursive to explicit because we can see the a sub 1 and the r right there. So my formula would be a sub n equals 3 times 6 to the n minus 1. And now if they want me to find the 12th term, I'd plug in 12. 3 times 6 to the 12 minus 1. Again, you could do it like that right there, but after the caret key, make sure you put that in parentheses. I recommend 3 times 6 to the 11. Less places to make typos in your calculator. But that I did, in fact, just type into my calculator. I got a really big number, 1,088,391,168. Okay. So from today, you want to be able to look at a sequence and determine if it is a geometric sequence or arithmetic. Are you adding or multiplying to get to each term? And once you identify it's geometric, we want to be able to write the recursive formula and the explicit formula. So we would need to be able to find a sub 1 and r to do both of those things. And last but not least, you'd want to be able to find a future term, like the 12th term here, which means you would need to take the explicit formula and plug it back in. Before you go ahead and pause this. Make sure you have all these key examples and information down on the note sheet. And then you should go and work on the 6-4A Pearson practice. Thanks and have a great day.